Welcome to Chapter 6, Section 2. This is Conservation of Momentum. So what we're going to do is we're going to describe the interaction between two objects in terms of their momentum. We're going to compare the total momentum before and after. We'll look at the law of conservation of momentum, and later we'll use this to predict final velocities of objects after collisions if we know their initial velocity. So anytime objects collide, momentum is transferred. So if we look at this picture here, we have this red ball here, and it's going along at a velocity, and our blue ball's just sitting. Then they collide, and then the momentum is transferred to the blue ball. So here the red ball has all the momentum and all the velocity, and then it's all transferred to the blue ball. So we have all kinds of transfers of momentum in everyday life. If you're bowling, the momentum of the ball is transferred to the pin. Car wrecks are a very common example of how that can happen. One car hits another, causes it to change direction. Okay, if we knock over a glass of water, we've transferred some momentum to it moving and falling over and the water spilling. And even a gun, it starts out stationary, but when it explodes, there's momentum. And it is transferred to the bullet and some to the gun as well. So when we look at conservation of momentum, then we've got to think about what that word means. And conservation just means to keep constant. Whoops, I can't spell. Sorry about that. Let's rewrite that whole word. Constant. Okay, or stay the same. So when we say that momentum is conserved, we mean that from before a situation till after a situation, the total momentum, okay, that's key here, total momentum is conserved. And this is true both in collision, when things run into each other, but also when objects push away from each other, like a gun. Okay, a gun explodes, the gun is pushed back as the bullet is pushed forward. Okay, in each of those situations, momentum is conserved. So let's look at this example again of the ball, and let's imagine that the mass of these balls is the same, and they're both 1 kilogram, because that will make our calculations easy. So then if our initial velocity of the ball here is equal to 2 meters per second, okay, and this one has an initial velocity of 0, then the initial momentum of the red ball is equal to 2 kilogram meters per second. Okay, because momentum, remember, momentum equals mass times velocity, so our 1 kilogram mass times our 2 meters per second gives us 2 kilogram meters per second. The mass of the blue ball at this point, okay, or the momentum, excuse me, is 0 because it has a 0 velocity. And these are our initial conditions. Okay, now when they collide, the velocity here of the red ball becomes 0. But the velocity of the blue ball now, and it's its final velocity, will be 2 meters per second. So we've transferred all the velocity from one ball to the other, and all the momentum is transferred. So then here we get the final conditions, and the momentum of the red ball is 0. Okay, but the momentum of the blue ball is now mass. Okay, and they both have this mass of 1 kilogram, so 1 times 2 ends up being 2 kilograms per second, or meters per second. And those are our final conditions over here. And if we total those up, right, if we add our initial conditions, we have a total momentum of 2. And over here we have a final total momentum of 2. And these are equal, so it is conserved. So one way that we can say this mathematically then is we can say the momentum of some object initially, so A just means some object A, plus the momentum of some other object. You take all of their initial momentums and add them up, they will equal the total momentum of the objects after they collide. So we're going to say those are the final momentums. And that's any objects, okay? And really, we could do this with any number of objects, but we will only calculate it with 2, okay? But it does apply to any number of objects. So we'll get a chance to practice the math on this in class. The last note is I want to point out that this really comes from Newton's third law, and we connected it a little bit to Newton's third law before, but if instead of one ball being stationary, or even if it wasn't, if you imagine them crashing into each other like in this picture, okay, the two balls are flying towards each other, they wreck, they crash, okay, and during this time, Newton's third law tells us that we get an action-reaction pair. So the force of ball 1 on 2 is equal to the force of ball 2 on ball 1. Okay? And because of this, because their forces are equal and the amount of time that they crash is equal, remember we have our impulse equation. Since these two are equal, then in this case, our change in momentum will be equal, which means the mass and the velocities afterward, okay, it will end up being conserved. So the velocities themselves won't be equal because this is a change in momentum. But because of that, we will end up with a total conservation of momentum. All right, I hope that you understand a little bit more about conservation of momentum now, and if you have questions, make sure and ask me in class.